Hello everyone, this is lecture 10 of PTRE 475575. Today we should be starting finally module 2. Before we do start it, because the deadline of the homework is due tonight, and I had some emails on the weekend, and I realized that you guys were not taught last semester how to build a polygon. I guess I had a homework that we were supposed to build one in, and it wasn't used in the last semester during geomechanics. If you guys have any question, please let me know. If you think you cannot make it tonight, please let me know before the deadline. And if it's a lot of people, I can extend it for a couple of days or something. But if you think you're doing it, it's okay. Some hint I wanted to give today for the homework. Let me open it. So some things I don't explicitly say, and maybe it's good to know, since I guess you are gonna spend more time on the polygon than what I was hoping you will. I thought you would get the polygon very quickly, and then at the other lines, spend the remainder of the time on the other lines. But the idea here is that you are gonna create a plot that looks a lot like slide 54 of module 1. Was it 54? Slide 53 of module 1. This plot here, the first one. This one. Oops. Somebody messaged me. Yeah, so I was hoping, based on what I thought, because I thought you already have been trained to drawing polygons, is that you will get this line very quickly, and you should be getting it. This is y equals x. Okay, then you should draw this line, draw this line, draw this line. Once you are at that stage, you just need to add three more lines. Okay, the other one, the first one of those is this, which is sigma z equal to 0. And the other one is this, sigma theta equal to sigma z. For those two lines, what you need to do is go to slide the equations for the vertical stress, 42. 42, and you basically, come on. These are the equations. You take this line, you set it equal to 0, and then you do the same thing as before. You divide by SV. So what is going to happen is that this will become 1. This will become y, using inverted commas because what is on the vertical axis. This will become what is on the x-axis. And then this is a value. I gave you SV and I gave you PP, so you divide like something like 0.433 divided by 0.93, you get something close to 0.5. Okay, and you have a value for Poisson's ratio. Now for theta, you need to think about it. Remember that the condition that you are trying to mimic is sigma ZZ is less than 0, and sigma ZZ is less than sigma theta. So what you are gonna do is ask yourself, which theta gives me the lower sigma ZZ to increase my chances? And you're gonna have a value, either 0 or 90, because those were the extremes. Theta would be, it gives you the maximum value at one theta, it gives you the minimum value at the other theta. Everything else is in between. So you need to do that. Once you do that, you rearrange the equation, you solve for y equals something x plus or minus something else, a constant. And you plot that line. Okay, mx plus c. You plot that, And that is basically the red line on this plot. And it's red, it should have been blue if it was me, but anyway, it's this line. For that line, sigma z, oops, sorry, my bad. For that line, what we will do, we will take this sigma zz, equate it to this. What am I doing? Sorry, guys. Take this, equate it to this, and do the same thing. Divide everything by SV, and then rearrange such that you get y equals something times x plus something else. And plot that line, and that will be the other line. And then the question that you have to answer is, okay, what is the region where both of those conditions are true? And you can use trial and error, but you want this to be true, which is in this side of the line, and this to be true, which is on that side of the line. I should have used a different color. But where do those two regions I drew coexist? And the answer would be this yellow region here. And then it's asking you, oops, sorry. It's asking you, how do you constrain SH max? SH max is gonna be read on the y-axis. SH max over SV, but you have SV. So you can multiply what is on the y-axis by SV and you get the range. But this is not enough. Because in the homework, I'm giving you an extra piece of information that is very, very important. And that is the value of SH mean. Because I'm giving you the value of SH mean, I'm telling you what will be the value on the horizontal axis. Like it's like I'm giving you the equation of a line x equals 5, or x equals, in this case, x equals 0.91 divided by 0.93. So I just say it's something like 0.95. How would a line of SH mean equals constant look like on the polygon? What do you guys think? How do you think that line will look like on the polygon?
Will be the red line, the thin one that cut the whole graph from 0, 0 to 3, 3.
Okay, it cuts it in what ways?
Diagonal,
Diagonal? Why?
because at the thin red line at the first paragraph, the thin red line, it's shear max equal shear min. Yeah.
Yeah,
So
but
you give us the shear minimum, and then we will equal it to the same value. So we will have the red thin line from 0, 0 to 3, 3.
I'm giving you SH mean is equal to 0.91. And I also gave you SV is equal to 0.93, right?
Also, it will be horizontal, I guess, right?
Horizontal?
I'm not sure, though, yeah.
If I give you a plot x equals 3, how does that line look like on a y-x plot?
Oh, it will be a vertical line with a
Yes,
constant
sir.
value. Yeah.
Yes, sir. Very nice. Vertical. So it's going to be something like here.
Right, 0.91, yeah, before the
Okay.
one.
And now you can constrain this yellow region even further. So the whole yellow that you see there, it will only be this little part here. Then you take this little part, you read from the vertical axis. What you read on the vertical axis, that range, this little range, you multiply by SV, and that's the answer. That's the range I'm expecting, basically. And that's a very real problem, actually. It's a real well in Gippsland Basin in Australia. And this is the method that they use exactly to constrain SH max in this region. Like 100% real world problem. But yeah, I was hoping that the polygon part would take not a lot of time, so the rest would be for the lines. And to be honest, the red line in this plot, and I'm always talking about the plot on the left, it's very easy. It's fairly easy to draw. The other one is slightly more difficult, but the last line, the one that is vertical, as you said, you need to think about it a little bit. And then if you end up in a situation where you don't know where you draw the yellow region, do what I was doing when I was young, take a point on this side, check it using the equality, check if it's bigger or smaller than 0, and then take a point on the other side and check it. And then you know which side is the yellow region. And do the same thing for the other line. And you'll understand where basically they all coincide. And then you know that this field, you know it's SH mean, and you know it's SV. So you know it's going to be somewhere, like Shamel said, on the close to here. Sorry. Let me use a different color. I will use dark green. You take it here, you move it up. So you know it's going to be on that line. So you see the range that you can get is from, it's a small portion of that yellow region. So you color that, you see how much it extends on the y-axis, and then you are good. Just remember what you are reading on the y-axis is not SH max. It's SH max over SV. So you need to still multiply by SV to get the SH max. Any questions? Okay. I should still be available. I have to meet somebody after this class. Well, I don't have anything from 2 to 3. I have something from 3 to 4. And then I'm meeting a student later. So after 6:30, I will be home. And I should be in front of if I get an email or something, I'll be able to respond to it. But yeah, I think I gave you enough hints to basically, we just need to go out, open a spreadsheet, and do it at this stage. Anyway, now we're going to start module 2, which is one module that the students like more than module 1. They find it more interesting, it's more practical, it's more hands-on. But it's not very, it's useful, but it's not very vital in a sense of a lot of the stuff we are going to be discussing. Well, it's very important, but it's not like on a fundamental level. Because a lot of the stuff that we are going to be discussing are stuff that change with time. Okay, technology, it changes with time, it improves with time. We have better tubulars now than what we had 10 years ago. We have better equipment. We have better items that go into our wells compared to other stuff that we had in the past. And I will we'll go over stuff that humans. It deals mostly. If I could label something in this module, we deal mostly with human-related, like things that humans make and put down the well. You know. Whereas in the previous module, we are dealing about natural stuff like the stresses, tectonic stresses and stuff. These are not dependent on the humans. But what kind of casing we use, I cares. different equipment we use during stimulation are very, very anthropogenic, let's say. Okay. So, general well completion methods. So, when we have several ways we can complete our well, we have drilled the well and we want to set it into production. So our completions people are dealing with it now. The drilling people turn it over to the completions team with a well filled with brine at a balanced condition, as we learned in drilling. And you are ready to hand it out to the production people to start producing the well. They will delineate, do some stuff to it. But before that, there is some things that we are gonna do to the well. Most likely, we are gonna try to stimulate the well to improve its production. But there are other things we can do. So the easiest kind of completion, the most simplest kind of condition, is the barefoot completion, as we call it, or the more scientifically speaking, the open hole completion. You leave the bottom of the well open, open hole, completely exposed to the surrounding nature, I guess. That's one way. Another way is that you will case and perforate. So you will run casing until the bottom. We are going to call that production casing. And in this casing, you are going to go down with a perforating gun, which can kill, but it's not a real gun. Well, I guess it shoots, so it's a gun. But anyway, it will perforate, create some holes and some perforation tunnels. And then those are going to be assisting the production. You're going to create, through the perforation tunnels, you're going to create conduits of fluid moving inside the well from outside. Okay, more sophisticated type of completion, and there is a reason why you may want to use that. Okay, we're going to discuss about those. Another way is gravel pack, open hole gravel pack completion. Gravel pack, when you hear gravel pack, think of filtering. Something is coming into the well that you don't want it to get into your well. Okay, something like sands or fines, as we call them, fines migration. Those little sand particles that move into to your well, but you want to keep them out of your well for several reasons. They can damage your casing, they can damage your separators on the surface, they can cause a lot of problems. So you don't want that. You create some artificial sort of filter that will keep those out. That would be the gravel pack. And then the ultimate vertical well completion was the fragment pack. There is a lot of those in California. You create a fracture, a big longitudinal fracture, axially oriented with respect to the vertical wellbore. This is the wellbore, this is the fracture by wing, and you fill that fracture with sand. And basically the fracture acts like both the vacuum that brings in the fluid from outside, but also the filter that will keep the sand from moving in, the fines from moving in. Frag and pack completion. A lot of work on those in California in the 80s. I know some people who worked on those, on the fracturing side of this. Now, that's one sort of category, but and it involves casing, okay? You're going to be having your production coming through the casing. However, this is not the only time, many times, our production doesn't come from casing, but from tubing. Okay, you're gonna run tubing inside the casing. It's sort of running like a, imagine I have a sweet tea here from Chick-fil-A. Imagine if it has a thicker straw, like a straw that they give for milkshakes and stuff. And then I put a smaller straw inside it. Okay. Then I can consume the beverage from the smaller straw or the bigger straw, okay? Or both, I guess. But there is a reason we use tubing. And in that case, several times that you might have a corrosive gas coming in, and you don't want your casing to be damaged. You want your tubing to be damaged because that can be replaced. Your casing is to stay there forever, okay? So you don't want it to be damaged. If there is some corrosive fluids coming in, those better be coming through the tubing so that they can, after some time, you can replace the tubing. Of course, it's going to cost money, and you're going to need a workover to fix the well, but still, I mean, you are going to, I would rather damage my tubing than my case. What holds the tubing inside the casing steady is something that you learn in production, which is packers. And we're going to see those a little bit in this module. You're going to see some stuff from production in this module. And the way the packers are set is very important. We're going to get to it later in the module. But also you may have multiple zones that you want to produce. And maybe you don't want production from those two zones to mix. There is several reasons why you may not want production from these zones to mix. But you can achieve that by what we call a shotgun completion. The official name is dual tubing completion with packers. Basically, you have, let me write on the screen to make things clearer. So you have this zone producing through this tubing, this zone producing through this tubing. You have tubing completion with annulus packer, one, and the fluid above the packer doesn't interact at all with the fluid below the packer. So if this is corrosive, you're protecting everything here. Everything is protected from by using a tubing with packer. Here, tubing completion without packer, it's a little bit of a, I mean, there are reasons you might want to use it, but it's, yeah, it's possible. I have seen injection wells that were injecting without packer, believe it or not. And I have seen a lot of injection wells that were injecting with tubing. In fact, they do it for safety reasons. Things that we discussed in the previous module, like most wastewater injection wells, they use tubing. And they use tubing to protect the casing, cement, rock formation system from the increased pressure by injecting. Because when you're injecting, it's the opposite of producing. When you're producing, you want the pressure downhole to be as small as possible. So you want very small bottom hole pressure. When you're injecting, it's a very high bottom hole pressure. And you can cause damage in the casing, damage in the cement, damage in the rock near the well. Those would be detrimental. So many times you are using tubing that can hold very high pressure. So the injection is done through that. And some people, they use they just from the case, you know? Completion engineers work closely with surface facilities engineers to ensure the surface equipment can handle the expected production. I mean, if you're expecting a lot of sand coming out of your well, you certainly want the surface facilities people to know so that they use specific equipment. Same thing if you're expecting acidity, like sourness in your production. We call it sour if it has H2S and CO2 in it. We call the oil, the produced oil, sour. If this happened, it causes issues, corrodes like tubulars, etc., etc. You want them to know. You want them to know also for safety reasons. You know, they say all the deaths from H2S, or the majority of them, they happen in pairs because your body goes down and then you go in there to see what happens. Even you go down too. Big problem also during drilling, etc., etc.
I have
There
a,
is a field. Yes, sir.
I have a question, Professor. So, which type is popular in the Bakken formation with the horizontal wall? Is it the cased and perforated only?
Well, you can have several. Whether you have tubing, yeah, but the second one here, case and perforated,
Case
is very
perforated.
common.
Okay, all right, thank you.
Yeah. There is wells that they leave them without production casing, actually, as well. Yeah, it's a big issue. Sour. There is a field in Kazakhstan that Chevron was working on, and they were producing a lot of gas that had a lot of sourness in it. It was like sour gas, and they wanted to re-inject it into the gas, the field. It was the Tengiz, I think, field, which is huge. It's the biggest field in Kazakhstan. And Chevron, back when I was a student, they had to make a tremendous design of facilities that would be able to handle the sourness of coming from that well. Otherwise, if you have to treat it, if you have to treat what you produce before you re-inject it, you know, it changes economics completely. Okay? In California, if you go to Long Beach and you look into the coast, you will see some man-made islands. They look like touristy places, but they are not. It's camouflaged production platforms. It's like 4 islands. They have like 1,000 wells in total, more than 100 wells each. Like, if not more than 1,000 wells each. I don't remember, but certainly there is more than 1,000 wells there. And they start from they have a rig that moves on rail like a NASCAR track, like oval, and it drills wells or like completes wells, etc., etc. And what they do is that they get water from the city and they inject it down hole. And they are mandated by the city to inject 5% more than what they produce. So if they produce 100 barrels of oil, they have to inject 105 barrels of water. I went there a few days before COVID, actually, maybe February. I want to say February 10 or 11 of 2020, something like that. Very it's a big process, and they do not what do? They do not treat the water before they inject it. They inject it as is. And there is workover rigs that are permanently on location, like semi-trucks that are on those islands on permanent basis, and they are injecting water to produce oil. And their water cuts are huge, from my understanding. Anyway, and that's the reason why for that rule, 105% more is because there was a lot of subsidence in that area. And some people say it's because of oil production. Some people say it's for other reasons. Probably the answer is both. But that area has subsided tremendously over the years because that field was the Wilmington field, the East Wilmington field, was produced very aggressively back in the old Hollywood era. It gave some people a lot of money. And yeah, so they are trying to sort of balance the situation now by injecting more. Injecting more water. But imagine if they had to treat that water before they put it in, it would have been completely different game, completely different playbook, sorry. So completion engineers also have to work with drilling engineers to ensure the wellbore architecture can sustain their completions aspirations. So if you are planning to have a certain production from that well, okay, you need to basically make sure that the well is drilled a certain way so that the production, your desired production casing, can be set. So if you want to design a well for a 2 and 7 inch production casing or production tubing, don't make it so that it can only fit 2 and 3/8. Okay, then it might be too small for the production. That you are aiming at. So you see, completion engineers are a little bit of a glue between drilling people who don't like to talk to anyone else other than themselves, and surface facilities people who are close to the wellhead, and production people, yeah, those are close to the wellhead, and make good they want their production from their well to be maximized. Okay. There was this old story I used to say, I don't know if it makes sense, but somebody said that the best car ever built is something like it's the Corolla, but we are in America, let's say Camry, Toyota Camry. They said it's several people, they sat together, they integrated everything, chassis, engine, base, tires, whatever, and they built the best car ever built, which is a very boring car called Camry. And then they took the engine, they took some part of it, and they made a new chassis for it. It was like the coupe version, I think it's Solara, something like that. And the balance on that car wasn't as good as the Camry because you mix and match, It's the same thing here. The completions people need to work with both sides of, all sides of the upstream business, from drilling all the way to production and surface facilities, to make sure that that everything is in place. Anyway, so parameters controlling your decisions when it comes to well completion design. You are a well completion for a certain operator, well completion engineer for a certain operator, and you are going to design the completion of a well. What are you going to consider? Wellbore trajectory, obviously. If the wellbore is has a certain trajectory, it will influence your design. Is it a vertical well? Is it a horizontal well? Is it a very, very directional kind trajectory? What is it? Wellbore architecture in place, what kind of casing you have, what kind of intermediate and surface casing you started with, etc., etc. What are the reservoir properties? Also, geomechanical and petrophysical properties play a role. Are you planning to frack that well? If you're in America, most likely you will. Virtually everywhere. If you're in another place, maybe it's good enough. You don't need to. The permeability is good enough. Are you gonna? Are you dealing with a carbonate and you are planning to inject some fluids that will interact with the reservoir badly? In that case, yes, you may consider using tubing, you know, etc., etc. Available surface infrastructure. Are you having a gas pipeline nearby, or are you gonna flare the gas? Gas flaring is a little bit of became a big topic, but I think it's bigger than what it should be. Because in some places, including West Texas, many parts of West Texas, flaring is the best option. You know, I would rather have CO2 released into the atmosphere than CO2, CH4, flammable CH4 or anything else. But because there is the visual aspect of it, like you drive by, you see the flaring. Many places you drive at night, you don't need to turn the lights of your car on. Bakersfield or West Texas, sometimes it's just, you know, it's good enough from the light from the flares, but ultimately that's wasted natural gas that basically is being vented, it's being burned with the produced CO2 going into the atmosphere. And finally, what are your field development plans? Are you gonna go for a water flood? So you have some wells that are gonna be used for injection and some others for production? Are you gonna do, like we said before, hydraulic fracturing? What is your plans to develop the field as a whole? I was talking to a friend recently, and you know the horseshoe wells, which is a modern design. They have a well that you drill vertical, you go like this, and then you turn, and then comes back. So it's like a, how do you call it? Goes like this, and then comes back. So you have two laterals. And they fracture both sides, but they don't fracture the U-turn. That company that he works for is doing a J-hook well. And the only reason for that is the way they are leased. Their lease is the specifications of their lease. It made more sense to drill a well like this. Very, it's like specific based on the contract that you have and the lease. But everything plays a role. What kind of casing you are gonna put, what kind of completion you are gonna aim for, what kind of tubing, what kind of configuration between casing and the tubing. Everything matters. Everything matters and needs to be, like we say, planning is the mother of success. Now, modern day completions, and this is something that this class is spending a lot of time on because the graduate students of this class, they are registered in this lecture, are registered for what we call advanced stimulation techniques. So modern day completions in the US in particular, but also outside, they are done using a certain multi-stage design. Multi-stage hydraulic fracture treatment design. And basically, you divide the well into several stages. You divide the lateral, into several stages, from the heel to the toe, several stages. Stage 1, and -2, and -1, and so the bigger the number of the stages, the closer you are to the heel. The smaller the number of stage is, the closer you are to the toe. I think I said it inverse earlier. Imagine the lateral is like a foot. The heel is here, the toe is here. You go from toe to the heel, the way you are going to stimulate them. And every stage has multiple perforation clusters, okay? And every perforation, this is a perforation cluster. This is a perforation cluster. This is a perforation cluster. And those perforation clusters are they have a number of perforations per cluster, and those will be stimulated all at the same time. Every stage, every frac stage is stimulated at the same time, at once. We stimulate stage 1, we stimulate stage 2, stage 3, stage 4, stage 5, and so on. The way that they are being isolated is using packers or some other methods we are going to see later on using videos. But when those perforation clusters are stimulated, not all of them induce fractures, can induce fractures. So if I have seen 60 perforations per cluster, okay? Somebody told me about more than that, okay? Doesn't mean I'm gonna get 60 fractures from those perforation clusters, okay? Many people who do simulations, they assume something like one big fracture per perforation cluster. We call that the dominant fracture theory, actually. So, the way we stimulate this well, so we have items like stage spacing, perforation cluster spacing. That's something I worked on for my master's. I was telling you last time about my master's thesis was about uneven perforation cluster spacing, okay? But those are all parameters you can play with to optimize your hydraulic fracture treatment. And ultimately, you want to place the stages next to each other. As close as you can put fractures next to each other, the better it becomes. The higher the production, the better the recovery from that region, you know? So this is how we go: stage 1, stage 2, stage 3, stage 4, etc., etc. Now, what did I miss? We have time, multiple perforations per cluster, multiple cluster per stage, multiple frac stages in each hydraulic fracture stimulation treatment. This is the gist of it. It doesn't mean that these days, well, I would say back at the beginning of the decade, there was a lot of talk about parent-child well stimulation and zipper fracs. When you have two wells next to each other and you try to go like 1, 2, 3, 4, 5, 6. They were trying to find ways to play with it, their stimulation sequence. Also, within one fracture, one horizontal well, another method of alternative spacing was called, it became known as the Texas two-step. It was invented by a professor at the University of Texas and his PhD student. The student's name was Russell. He was French. And the professor's name was Sharma. Around 2012, 2011, I was still undergrad. So the way they go is that instead of going 1, 2, 3, 4, you go like 1, 3, and then 2, and then 5, and then 4. So the way this is done, it was shown that the way the stresses are affected in the well, when you go to fracture, when you go and do those treatments, it's very favorable. So it creates more even spacing. Now, any questions so far? Okay.
No.
Oh, okay. Since we have talked about this is a complicated process, the operation of hydraulic fracturing in a horizontal lateral. We also talked earlier in this class, and I believe you also talked in geomechanics, that longitudinal hydraulic fractures from the horizontal lateral are a bad idea. Okay, it's a bad idea, but sometimes there is not many options around it. But the way a fracture, when you get a fracture initiating, instead of the way the goal is something like this, and you want to have fractures transverse. So it's like the one is like this, boom, 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 boom. And you get something instead that looks like so those fractures are basically like this, longitudinal, axial with respect to the wellbore. What will happen when they grow is that they will all merge with each other and they will create something like a gigantic longitudinal fracture. And the problem is that one longitudinal fracture does better than one transverse fracture, but multiple transverse fractures won't do better than one gigantic longitudinal fracture. So you need to, you're trying to create this, not the bottom, not what I have on the bottom. What happens now is that if you drill your lateral parallel to what we call SH mean, if you are in the normal faulting or strike slip faulting stress state, this should be the best way that you can drill your well to promote transverse fracture initiation, hydraulic fracture initiation. But it may not be enough. It doesn't mean that if you drill your wellbore parallel to SH mean, you will have automatically transverse fracture initiation. Because as we know, we may go to the previous module, and we see what happens when we are drilling a well, and when you are drilling a well, you are stimulating the well, you are basically disturbing the stress field surrounding it. You may create a stress field that favors longitudinal fracture initiation. So when the fracture initiates near the wellbore, let me go back to module 1 slides very quickly. Oh, don't tell me I closed them. There was a picture from Economics book I wanted to show you, which is, sorry for the black and white image, but ultimately, what happens here, I'm talking about the bottom picture here. The fracture started longitudinally, and then the stress field took over and forced it to twist. So it became correct as you went away from the wellbore, but it was bad when it initiated. This is not good for several reasons. It creates what we call near wellbore fracture tortuosity, And it is manifested as several problems like incompletions and stimulation. For instance, here is a picture of a tracer test. They ran a tracer test during a hydraulic fracture treatment. And it was presented in a book, in a paper by Barry and Miskinis. Barry is a consultant, private consultant right now. He wrote a program for fracture modeling, and he sold it to Halliburton for a lot of money, people say. It's called Gopher, Gohfer, and now it's the Halliburton Gopher. But he's still working as a consultant. And Miskinis is Jennifer Miskinis is the chair of the Petroleum Engineering Department of Colorado School of Mines. And she teaches a class very similar to this one. And she's going to be in our campus in the 23rd and 24th. She's visiting us of this month. So next week, next Monday and Tuesday. I saw her when I was in Golden last Christmas. I was at the cafe, and I was with Lun Snee, and we were waiting in line, and she wanted to pass over, and she said, "Excuse me, guys, can I?" To let her pass, and yeah, she didn't. She knows me, but she didn't recognize me at that time. But I was busy with my discussion with Lun Snee, so I didn't want to interrupt her. Anyway, so in this paper that they presented, they see fracture from one stage, like yellow fluid from stage 1, appearing at stage 2 and stage 3. Okay, and red fluid from stage 2 appearing in stage 1 and stage 3, and blue fluid from stage 3 appearing in stage 2 and stage 1. This shouldn't be happening. You really want the fracture for a specific stage, fracturing fluid for a specific stage to stay at that stage, okay? Not to interact, move around. It creates inefficiencies if it's moving around. It tries to propagate existing fractures instead of creating new ones. And we call that stage communication. And this is very much what's happening here. And actually, Barry and Miskinis blamed it on longitudinal fracture initiations near the wellbore. Poor frac stage isolation, localized stress interference in the near well vicinity. So several, we will see a little bit more in the next module, but every frac stage, almost every frac stage ends with something called screen out. Okay, you end up in a situation where the propant bridges in a certain way that you create, you can apply a lot of pressure on the surface. It doesn't get transmitted down hole. Okay, so you pump as hard as you want on the surface. There is no transmission of that pressure down hole. We call that screen out. If it happens early in the stage, it's bad. It's bad. It means that it doesn't let you fracture that stage. And again, there are ways you can mitigate that, but it's a bad idea if you get early screen out. And another problem is that the stimulated well is not producing as well as you are expecting it to produce. You have simulations where it was saying that the well will be producing X amount of barrels per day, and is producing X minus something else amount of barrels per day. The reason for that is the low, those longitudinal fractures that created longitudinal fracture initiations that created near wellbore tortuosity. So here is an example of that early screen out I mentioned earlier. We see the pressure on the bottom. This is BHP, bottom hole pressure. And look at the pressure on the surface is this. Only look at the red lines. Blue line is the rate, and the green line is the surface pressure. You don't care about those. You only care concentration. So you only care about the dotted red lines. So look at the surface pressure. What happens at minute 32? You spike the pressure. Okay, you are pumping as hard as you can on the surface. You are here. And what happens to the pressure downhole? In the BHP, it goes down actually. That's because you breached, the proban breached, and you're basically not transmitting pressure from the surface downhole. Proban breaching, forcing a total screen out. So you're not really creating fractures or propagating fractures. You're just like damaging your equipment on the surface. This is a bad idea, and it's possible because of those longitudinal fracture initiations. They create near wellbore fracture tortuosity, which in turn damages the effectiveness of your stimulation operation, multi-stage stimulation operation. Any questions?
No, Professor. Thank you.
Okay. If you have, let me know. I'm asking if there are any questions because I'm about to switch a little bit subtopics now. But the next one, you have already seen it before. You have seen it in drilling, advanced drilling, and now you're going to see it in this class. I don't think we show that in geomechanics, but it's routine pipe calculations. Basically, when we are dealing with tubulars, we want to know how much fluid these tubulars can keep. So that we know if we are pumping a certain amount of fluid downhole, how far this fluid has gotten. It all plays a very important role. Say that we have a pipe that has inner diameter of ID, inside diameter, inner diameter. And we want to see how much we can fill this pipe, how much fluid we can fill this pipe. So I'm only talking about this basically. What's the capacity? How many barrels every foot length of this pipe can accommodate? And you are going to use a very famous conversion factor for that. It's 1029.4. So ID square in inches divided by 1029.4. Now, where does this comes from? You know the old cross-sectional area, the equation for the cross-sectional area of a cylinder is pi r squared. It becomes pi diameter square divided by 2 square, which is pi diameter square divided by 4. Why do I prefer to use diameter square instead of radius square? Is because the diameter is easily available to me. In the field, nobody mentions radius. They will mention outer diameter and inner diameter. It's and the reason why nobody mentions radius is because you cannot measure radius directly. You cannot go with the vernier calipers and be like, I will measure half of this opening. You measure the whole opening. Okay, you divide it, but you cannot like move the caliper up to where you think it's half, you know? So pi d squared divided by 4 is a more practical equation. And then you are given the ID in inches. And 1 inch, if I want to convert from inches to foot, is to feet. Inches squared to feet squared, I divide by
12.
say
12.
12 square.
144.
Yeah. ID square. Notice here, it's ID square. So 12, you divide by 12 and then you divide by 12 again. So it's like inches square to feet square. This is 144 to 1. And then you have something like feet square. There is feet times feet is cubic feet, right? 1 cubic foot, how many barrels is, sorry, let's make it different. How many cubic feet per barrel? One blue barrel is 5. Oh, sorry. 5. What am I doing? Stop writing. 5.614 feet cubed at standard conditions. Very important. At standard conditions. So the way my conversion factor is ID squared in inches, and you do pi. Sorry, it's the other way. Pi over 4 times 144 times 5.615, something like that. So let me see. You have 3.142 times 144 times 5.614, okay, divided by 4. What am I forgetting here? 144 divided by, or is it 4 times 144 times 5.61? Oh, I use it. Okay, divided by 3.142. Here you go. So
So
this should be,
it should be 4 times 144 times 5.615 divided all by pi.
yeah,
Yeah. And I got a 1020.
1029
.49.
yeah,
Yeah.
there you go. If you want to look at the step-by-step derivation of this, which is pretty much, it's in the drilling book, the red color book, textbook that we use in drilling. But ultimately, this is a very important conversion factor. It's as important as that 0.052 that we did in drilling. I always say I'm not going to be giving it to the students when I'm making an exam, but I always end up giving it to them. But it's one I kind of want you to know as much as possible because it helps, understand. It helps to have it at the tip of your tongue if you are in the oil field. Now, annular space. Now we are looking about this part. So the situation now is you have fluid from here all the way to here. So the equation that you are going to use is very similar. This. Same units, barrels per feet length. And you multiply this by the length and you get the volume, okay, in barrels. So you know how much you pump. Or if you know how much you pump, you know how far down the well you have made. Now, I want you to notice something. In the drawing I did earlier, in the real world, you are dealing with walls. So what we call OD is basically an inside diameter of the casing, the bigger tubular, right? It's the inside one, so it goes from here to here, OD. So you are looking for an ID of the tubular to use as an OD. So it says OD here, but it's an ID value that you are looking for. And the opposite with the other one. Oh. The opposite with the other one is that you have an ID. Sorry, it's an ID, but it's really an OD value that you are looking for. So it says ID, but it's an OD because it's the outer diameter of the tubing. So please be careful. There is a lot of ways you can get confused here. But we don't want you to get confused like that. A lot of people get confused. And also, there is several ways you can skin the cat. Somebody can give you pipe weight and density. The density is basically the density of steel. Okay. Because outer diameter is very difficult. Sorry, inside diameter is less easy to know in the pipes. So we prefer if you know the outer diameter, the weight of the pipe, and the density of steel, because these are specifications that are easy to play with. You can find them in the Halliburton Red Book, etc., etc. I'm giving you here the density of steel is 490 pound mass per cubic feet, or something like 65.5 pounds per gallon. So water weighs 8.33 pounds per gallon. Steel weighs 65.5 pounds per gallon. And here is the conversion factor from earlier, the 5.614, 615. So you have seen these slides before. That's why I'm going a little bit fast. But yeah, if you have any questions, please let me know. I have office hours tomorrow, 11 to 2. I will have to cut them short, either start them late or finish them early, because I'm giving a tour to a student, a prospective student. So I will let you know with an announcement or something. But yeah, if you have to talk to me about something and you cannot find me, shoot me a message, shoot me an email, and I would arrange for a private Zoom call. As far as the homework goes, we will.
I think, Professor, I need
Yeah,
an extension with the homework for me. Yeah.
you will need an extension.
Yeah, if it's possible, we appreciate it.
Okay, let me see. Would by tomorrow night work?
I was thinking Friday night.
Okay, let me see. Friday night. Okay, let me see. What about Thursday?
Thursday, yeah, it's work. But kinda the information, the feedback that you gave us today, is this not how I did my homework? Yeah.
Let me see what I can do.
All right,
Let
thank
me
you,
see what I
Professor.
can do. I will send you. I will send an announcement.
All
Yeah,
right.
it's good to put it past. If I put it past Wednesday, that covers the office hours. I have one more office hours to help anyone that has issues. And then we also have one more lecture. If you guys have any questions outstanding, we can go over them at that time. Anyway, I have to go because the next class is going to be joining. Yeah, I will see you on Thursday. Thank you. Have a nice rest of your day.